Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
One of the reasons I was asked to actually introduce most of the speakers today. Sorry, I can get away with saying that, I guess, because I actually have worked very closely with both of them over the past few years. And there's also an interesting kind of history between both Fei and Hany. Both Fei and Hany are ex-IBMers. They both worked on machine translation for IBM. And so they in the same group, although for much of the time, I guess you were in Cairo, is that correct? And Fei was in New York, although there was a time where they were together in New York. And so when Hany was coming to our team, he says, "Do you know Fei Xia?" And I said, "Fei, I know Fei very well." So and then it was like old home week when you guys got to see each other again after a number of years. So there's that kind of interesting twist here. This was not planned. We didn't plan to actually have two ex-IBMers giving talks here, but it gets even more interesting because as you know, Hany works here at the machine translation team here at MSR, and Fei's co-author, as it turns out, is also a Microsoft employee. So we have a paper that is both being presented by two ex-IBMers and two current Microsoft employees, although Fei is not a Microsoft employee. I guess we'll have to work on changing that or something. But it was a hard. Hany started, I guess it was four or 5 years ago now. Yeah. And as I mentioned, he was at IBM before. He was worked on machine translation and information extraction. It was kind of a combined group. I also happen to know Hany's advisor from Dublin City University quite well, Andy Way. He and I are good friends too, and so it's kind of this other little bit in there as well. Unfortunately, I don't know what year your PhD was, but he got a PhD from DCU, so we'll just say that. And it was a real pleasure to interview Hany a number of years ago. He worked remotely for a year, and it was great actually having him come to the team. He's exceptionally productive on the machine translation team and does a lot of really cool stuff. And it's been a pleasure actually working with him on some of this cool stuff, like the text corrector and some of the other things. And this is something I didn't have the pleasure to work on, but I'll turn it over to Hany. The talk today is graph-based semi-supervised learning of translation models. Hany, the floor is yours.
Thank you. So thank you all for being here in this sunny day. So this work is a paper that will appear in next ACL. It is graph-based semi-supervised learning of translation models. The work done with Avnish Saluja, who was interning here last summer in collaboration with Christina and Chris. So in this line of work, we're trying to leverage the monolingual corpus. We all know for machine translation that we really need sentence-aligned corpus. We really need word-aligned corpus to learn translation rules. So we are trying in this work to challenge that assumption and measure how good we can learn translation rules for machine translation from monolingual corpus. We explore how to learn that from comparable corpus and even from monolingual corpus that is not related at all. So why we are trying to do that? As you all know, a lot of the parallel corpus on the web now are not really parallel. Maybe it is comparable, but not parallel. And the real parallel corpus are mostly now machine translated already, which causes a lot of problem and a lot of noise there. On the other hand, the monolingual corpus are really available in many domains, in many areas, and produced on regular basis for any domain. So if I am trying to, for example, train an Urdu-to-English system for medical domain, I can easily find monolingual data on both domains, but not that parallel data or even comparable data. As a note from our even very large machine translation system, we usually utilize, or any large machine translation system usually utilizes shorter phrases, not longer phrases. And the reason for that actually because we don't have enough data to learn the longer phrases, 2 words, 3 words, 4 grams or 5 grams, is very sparse and we can't learn that. So even if we have the phrase tables in our machine translation system learning 4 or 5 words, we are really at runtime utilizing 1 or 2 words at most, because it is very sparse and we can't learn enough statistics to have reliable long range or long span of phrases. On the other hand, for monolingual data, it is very easy to be learned and it is very cheap to get n-grams, similar to the monolingual language models. So the problem we are trying to tackle here is handling the machine translation learning of translation rule, similar to the way we are doing monolingual language model, using n-grams from monolingual corpus. In this work, we'll try to answer a few questions. One of them is very challenging. Do we really need sentence-aligned or word-aligned corpus to learn translation rules or not? And this is a very interesting point. The answer is no, if you are curious what is the answer now. So, which is a little bit surprising, but it is no. Second, how good those translation rules would be if we learned it from monolingual data? Because most of this work done before in that area, trying to learn out of vocabulary just to try to compensate for an OV word. But learning real phrase-to-phrase translation, like 2 grams to 3 grams, 4 grams to another 4 grams, is not covered in this area at all. So we try to evaluate how good those translation rules are. Can we leverage monolingual corpus, not comparable at all, that is not related to each other, to learn translation rules? We'll try to investigate that issue as well. And the fourth one is a little bit tricky, and it's been advocated for the machine translation community for a long time, that we really need very large language models, and that's it. If we have enough large language model, it will even get good translation from word-to-word translation without any need for phrases. So we challenge that assumption as well, and we will see if we really need language model or we really need longer phrases in our phrase table. As the utilization in phrase that we see in Arabic English production system, for example, is 1.4 words only, which means that we are utilizing unigrams and bigram only during translation. So if we learned trigrams, 4 grams that we really can use during decoding, would it help the language model interact with it, or the language model on itself will cover that issue? So we'll try to answer those few questions here. So this very high level overview for that kind of work. So simply, we start with a machine translation system that is phrasal, for example, translation system as usual. And the assumption that we'll have a very large graph. This graph will query for giving any gram here for the source, like 2 words, 3 words. We'll query that graph asking for translation for never seen bigrams or trigrams before. And those translation would be fed into the runtime of the translation system to continue the usual translation process. So in this talk, we are focusing on how we construct this graph to query it for any gram on the source to return any gram on the target. The work done on the runtime of the machine translation system itself is minimal. So we are only talking about offline processing here that can produce new phrase tables that can be used in any translation system. The translation system itself is, as usual, any vanilla phrasal decoder. So taking a little bit dive into how this graph is constructed, we start with a translation model here, which we need some parallel data to start with, even few 100,000 sentences, just to have an idea how this language map to each other. And we start with many sentences on monolingual corpus. In this monolingual corpus, we feed into the system, and we decide if we know those phrases or we don't know that phrase. Phrase means here, it is n-gram. So it is phrase with the definition of phrase-based MT, which is just a sequence of n-grams, no linguistics information, just any n-gram sequence here. And we end up, if it is labeled, mean do we know a translation for this from our translation table, or it is unlabeled, which means we don't know any translation for that mapping. And then we need to add this to our graph, trying to start the graph propagation and augment our translation model with those translations. So this offline process, when we try to enrich our phrase tables with new entries based on some given source. And again, we will show how we construct this graph to query those translations. So this is what our graph should look like. Again, this is two different graphs, one source-side graph, one target-side graph, independent of each other. And each one is constructed on monolingual corpus, not related to each other at all. And the main objective of this graph is to end up with translation distribution for each node on this graph. Each node on this graph is a phrase, bigram or trigram, for example, and the distribution is target phrases with their probabilities. As you can see here, the dark nodes here are known, mean labeled, or we know translation for them, and the white nodes here are unknown, and we don't know any translation for them. The main objective of that process is to propagate information through the graph to end up with distribution on those nodes similar to that distribution, and this would be added to our translation table. So again, those two different graphs, one constructed on the source side, one constructed on the target side. But as you can imagine, the definition of phrases here is very loose, so this graph can be very, very large if we consider all possible n-grams on a large monolingual corpus. So we have some restrictions on how we construct this graph, or some tricks to make sure it is still trackable even with high computational resources. So here we start constructing our graph from the barrel seeds that we have. And then we have some target nodes, which is phrases on the right side, some target source node, which other phrases on the source side. And that is the only link between the source graph and the target graph. But the source graph itself is constructed from the source side monolingual corpus and the target graph as well. If we restricted ourselves to those kind of nodes in that graph, means that we need to translate phrase A, that we never seen any translation for it before. We have only candidates from our phrase table, which is very inefficient, because that means we can translate some phrase to a similar target phrase to one seen phrase before, but we can't translate to new phrases that we never seen in the target. Again, if we're trying to translate this phrase A that we never seen in our data before, we need to translate it to some target phrase in the graph. And the graph constructed only from the parallel corpus is very limited. It doesn't have enough varieties to provide us with various translation. So we need to expand this graph further to have more candidates for those target translation. So the candidates can be from any initial candidates that we can provide, like bootstrapping from other the same baseline system, bootstrapping it to get rough translation for those phrases and add those to the graph as possibilities, or generating morphological variants for those phrases on the source side, trying to get similar phrases on the target side, and then we enrich that graph to have many, many nodes that we can be translation to that source phrase. Again, if we didn't do that restrictions, we will end up with very large graph on both sides, and it's still not computationally efficient to do that. For that, we do that restrictions to just make sure that we have limited space on the graph that we can propagate with. Any questions so far? Okay, so that is how we generate the candidates for our translation. Again, we have different sources for generating the candidate. First, assuming that we're trying to translate that phrase A in the source that we never seen, But this phrase has similar phrases on the source side, which is, we will show you how this similarity is constructed, but every source phrase is similar to other source phrases. So a possible translation for that would be the translation for those similar target phrases, which one possibility. The other possibility is the similar other targets to that target phrase. So now we keep expanding that graph to add similar candidates as well. Third possibility is morphological similarities that we generate on a stem level, similar candidates for the target, and we keep expanding the graph to have a lot of varieties there. We keep like the top n best candidates per source nodes, and from here, the main objective again is to propagate the probabilities and the distribution on all that unknown nodes. So now what I described so far, we only have the topology of the graph. So we know what is the nodes, and we know we know how they are connected, but we don't know even, we didn't define that connection yet, and we didn't define the weight on those edges yet. And this is very open issue. The second thing is we need to do propagation whenever we define the weights on those edges here. So the first, which is the graph constructions, what is the weight on those edges and how we construct it. This is very open questions, because you can have a lot of possibilities on how two phrases are similar to each other. For example, you can have distributional similarity, you can have vector space models, and you can have a lot of varieties that can derive a similarity between two phrases. Very open research problem, and there is a lot of work to be done there actually. Here in that kind of work we are introducing now, we are just touching the surface here, and that nodes or edges are very simple pairwise mutual information based on the context of the phrase. So for each phrase, we collect statistics from the monolingual corpus, the vector to the right, the vector to the left as a bag of words, two words on each side, and you construct a vector for each of those nodes, and the similarity, pairwise similarity, is the cosine similarity between those graphs. We keep 500 neighbors for each node in the graph, so it is a very dense graph. But again, the edge similarity here, we defined here, is just the pairwise mutual information, which is very limited knowledge for now, since it is phrases and it can have a lot of information, semantic similarity. It can even have like syntactic signature on the gaps, on the borders to derive some similarity. So there is a lot of work to be done here on deriving how the similarity between two phrases is. Again, the simple solution here is just pairwise mutual information for that work we are presenting. Second, we need, since we now have the edges here, everyone has weight, which is the cosine similarity, we can now propagate the knowledge on that graph to have nodes and distributions here. Means that we need to propagate the distribution on this source node from all possible connections to end up with a distribution like this for every node. And querying that graph later, we can have phrase translation for any given phrase. The propagation problem is easier, actually. Once you have a good dense graph, it is easy to do propagation there. We have two options of propagation here. The simple one, which is label propagation as usual. And here, the probability of that phrase having that being a translation of the source phrase in the iteration t+1, depending on you are coming from iteration t, that probability is just the summation of the weights on that neighbors for that node. This has some limitations here, the label propagation approach, because it only depends at one side of the graph. As you recall, our graph is a little bit complicated when we have two sides, source side and target side. The label propagation here will only account for the neighbors on the source side, but not the target side. For that, we prefer using structured label propagation. Structured label propagation is the same here as label propagation, but as you can see here, it has another term that propagating the weights for the target similarity as well. So while propagating on the same graph, we can have similarity on the source side, similarity on the target side in the same propagation mechanism here. So whenever we are propagating a translation, we are making sure now its source is similar to each other, its target is similar to each other using that propagation mechanism. Structured level propagation is very efficient. It only takes 2 iterations on that graph. This graph is composed of like 600 million nodes, and it takes only 15 minutes to propagate there. So it is very efficient. The computational bottleneck is in constructing the graph because, again, we are using pairwise mutual information to construct the graph with 500 neighbors. So it is very, very enumerative to do that computation. But on nowadays, larger clusters, it is easy just to utilize 500 machines to do that in a couple of hours. But still, it's computationally expensive. It is not cheap as any graph-based technique. So now, returning to that graph again, we ended up with having all those nodes having distributions, which is translation probabilities, and we end up querying all those to construct a new phrase table, and for that we can use it during translation. For our evaluation, we use 2 systems, Arabic to English and Urdu to English. Arabic to English is not resource low language, but we here simulate it as resource low language, but because it has a lot of corpus in real comparable scenarios, so we can measure how good when we have comparable corpus we can do versus non-comparable corpus. For the Urdu English, it is very low resource language, and there is few parallel corpus out there for Urdu English, and we examine more scenarios here. So that is the Arabic English training data for the parallel data, and that is the Urdu English, which is the nest evaluation data. For the comparable corpus, those are from the gigahertz corpus on Arabic and English, and those are really comparable data. It means that it's from AFP corpus, same months, so it is really similar to each other, and this will evaluate how we can really get from similar data, same source, AFP corpus, same months, though as you can see, all of the English is larger, but we assume that they are talking about the same events, same contents. For the Urdu English, this is noisy parallel data, means it is crawled from the web. It can have machine translation contents, it can have very noisy contents, but still this will give us an idea how we can utilize this data in that setup as well. And on the extreme here, we are utilizing as well Urdu and English monolingual corpus, not related to each other at all, just as we crawl monolingual corpus to build language model. So we'll evaluate the effect on those data as well. So just the analysis on why we are not tackling OOV issue as most of the work done trying to utilize monolingual corpus before. It is really not OOV issue, as we can see here from that statistics. That is from the def test here, number of sentences the def sets here. And here is the number of bigrams on those test sets. Unknown bigrams mean I have never seen that in my phrase table before. So this means that is almost 56% of the bigrams on the test and def set not ever seen on the phrase table, or not seen in my parallel corpus at all. So for more than 55 or 56%, we resort to word-to-word translation.
Is this, which language pair is this?
This is Arabic English.
Yeah.
So means that for those percentage, we resort to one word-to-word translation, and we depend on our reordering model, depend on our language model to put pieces back into order. For that, we are tackling the bigram issue here, trying to compensate for that issue. If we break those down as more like what is of those bigrams known and what is unknowns, known means that both words are in vocabulary. So we know that both words are in vocabulary, and in this case, we resort to having word-to-word translation. Known unknown means one of them is known in vocabulary, and the other one is really OV. Both unknown, which is very rare case. only from those 142. So our real focus on getting real bigrams that is even known but never appear together in our parallel corpus. If we can acquire translation for those, can be more reliable and it should enhance our system. That is the assumption we had. Should we tackle the OV problem or should we have bigrams, trigrams to compensate for that? For the Arabic English result, that is the baseline on NIST data. NIST evaluation, the def set is MT06, the test set is MT08, and the language model is like 50 million sentence, I think, on the target. So it's a small language model. And then we can see here the baseline, and that is when we use the graph propagation using 1 gram only. This case means that we are handling OV. And you can see here, it has almost no effect, or even bad effect on the test, and very small effect on the dev. So we really want to handle the bigram case. And on that case, that is using the label propagation, when we take into account the source similarity, but not the target similarity. It helps a little bit. Almost here 1 blue point or more, and here less than 1 blue point. And when we add the structured label propagation, and when we take into consideration the source and the target as propagation criteria, we get much more improvement on both the dev and the test here. There is an issue here, little bit question again, which we raised at the beginning. Since we are adding bigrams as one piece, should that be compensating the effect of the language model? Because if we have large enough language model, it can cover those bigrams. We have here like small language model. So what if we have a very large language model would be marginalizing this effect, or it will be add-on for the same effect? So we switched to using our very large production language model, which is built on like 9 billion tokens. And here that is the baseline with the large language model. It jumped like 2 blue points from here. And then we can repeat the system again, which is the best system here. And we can even see here the improvement is even much better than the smaller system. So that means that even with using very large language model built on 9 billion tokens, our production actual language model, very, very, very huge system, we still see the same improvement. This means that we really make improvement from having the phrase as phrase translation, not from the language model effect. If we are not seeing the same, so we really wasn't sure that will affect from adding those bigrams because we stick them together and we're compensating for the language model effect or not. But as we can see here, it is really not the language model effect, it is the translation mapping effect. Here we evaluated the comparable case because this data used in the graph machine translation based approach are the AFP comparable corpus, which is both are from similar data. So it means that we need to evaluate the other extreme case when it is not such parallel corpus. And we did that with Urdu actually. This Urdu, that is the baseline using NIST data. We don't have any graph-based approach here, and that is the dev and test BLEU score. And then here, that is another baseline, adding the noisy parallel corpus, which is crawled from the web, which give a lot of improvements here. Those are 160 K sentence, and those are another 450 K sentence. So it is quite like 4x that amount of data. But as you can see, even it is noisy, crawled from the web, it can give a good jump here. In that experiment here, we are trying to evaluate the effect if we are using that noisy parallel data as comparable corpus. So we remove the sentence alignment and we handle them both as chunks of comparable corpus. And we feed that into our graph construction system. We construct the graph on the source from the noisy, from the target and the noisy. And we try to measure how good we can learn compared to that system. So that is the baseline, and that is the translation rules added from handling this data as comparable corpus. And if we handle it as parallel corpus, because it's parallel already, we will get that much. If we are handling it as comparable corpus, we will get that much, which is very close to what we get from the parallel data. And this is very important observation here, because that means that we can learn without sentence-aligned data, or without even word alignment. These data are just n-gram extracted from those data, and we construct the graph using both of them, and we get translation rules, adding it to that system. As you can see here, we are losing a little bit, but the price is that this is not sentence-aligned data, it's just similar data, which is, I find this one of the most important findings of that work, actually, when we can get relieved from having very parallel data and try to extract from non-parallel data. That is another extreme corner here, when we just have monolingual corpus that we crawl using for the Urdu language model and for the English language model. We don't have any similarity between. They're very different domain, nothing at all. And we still can get improvement. This one would compare to that one. So we still have 1 blue point almost, and in the test 1.2 blue point between that and that one, which means that we even can learn from monolingual, not related corpus at all. So I found the Urdu-English case is much descriptive than the Arabic English, because it's really low resource language that we don't have any data for it. That is the only public available data for that language pair, and that is what we have, though we have a lot of crawling mechanism to get. That is all what we can get from the web for that language pair. So such small language pair can benefit from those approaches a lot. I am maybe out of time.
Yeah, but don't.
Okay. So I have a couple of slides here. So that is a few examples from Arabic English. Here, that is the pigram we are trying to translate, and it is not in our phrase table. The translation is with pigram, but it is 5 grams on the English side, the reference here. And our baseline just drops the president. So it should be US envoy of American of US president here, and then we dropped it because that is very usual in phrase-based translation, and when you have a lot of unknowns, the system prefers to be brief and drop unknowns, and the language model would prefer this more. And that's our system when we have US presidential envoy. As you can see, even the blue score may not have any different at all, because presidential is not president and so on. But this is much better, sorry, here. This is a good example, and that is a bad example. This bad example here, we have that this guy, person name, said blah, blah, blah. The baseline is very brief, he said, because we don't know him, so she's good, right? And then our system proposed another name, very similar name. Yeah. And this is the drawback of the pairwise mutual similarity. Both names will appear in the same context in very similar way. And we don't have any better features to model that here. So Abdullah and Awadallah, Will Lewis and Michael would be in the same context, right? That is the problem of very simple features that we used here. For that, we are moving away from the pairwise mutual similarity to more sophisticated features to have better weights and edges on that graph. For the Urdu-English, that is the pigrams, 2 words here. I don't know Urdu. If someone knows Urdu, let me know. And that should be, I am hopeful. The baseline, that's this hope. And we propose that I am hopeful, which is much better than this. Again, this is varieties of another examples that we have and where it came from. So here that is the Arabic itself as that, or sending reinforcement. The baseline, strong reinforcement, and we get sending reinforcement. N means that it is one of the neighbors. It is already on the graph somewhere. It is neighbor for one of the phrase translations there. But we can pick it as one of the translations. This is the same. It was OV in the baseline, but we can get it. It is one of the neighbors again. This was address in the baseline. We can get the correct translation. Different tense, but for phrasal system, it's okay. And then here that is very good one as well. Both are good. Even the baseline is not bad, but we are having better here. G means generated. Generated means either it is came from the morphological variance generation or from the baseline rough translation, but it wasn't not one of the neighbors. We generated it based on some similarity on the source. This OV, those are Urdu examples. To defend him, this is clearly this is morphological generated, and we get him to defend himself, which is much better, while speaking in the and so on. So we get a lot of those improvements that is really n-gram improvements, not OVs, not even the OVs is phrase OV, it's not word OV. So we get a lot of new phrases that we really propose new translation for it. So we hope that this promotes some new direction for machine translation, and when we get relaxed on getting more parallel data and maybe focus more on having more revisiting the graph-based techniques, which very efficient, but due to the computational cost, it didn't get into the game till later. But now with the more cheap computational resources everywhere, I think it is time to revisit such approaches. As we can see, once we constructed a good graph with good candidates, the propagation is trivial. More work on how we construct the graph is the important thing here. Our future direction here, we are actually switching to heterogeneous features. For the phrase pairs, we can have syntactic similarity. For example, CCG signatures. We can have semantic similarities. We can have continuous vector representation for the phrase, and then we get relieved from that pairwise mutual computation. So the phrase are just a vector. And this will give us new dimension for how we can construct our graphs. The features in that vector would be related to whatever you want to design there. The bottleneck here is that you need now to learn the similarity in a better way. So, and this is still future direction that we will try to tackle in this line of work. I think I'm done. So if you have any questions, and please see our paper in next year's ELO. Thank you.
So I'm lucky that I actually know Arabic and Urdu, but I noticed that you did very well in Urdu morphology where, so par umid means hopeful, umid, just umid means hopeful. I hope actually. So it's interesting
So
there.
what is par means?
Par is it's a morphology to change it from hope to hopeful, right? So it's a
Okay.
morpheme.
So, but it's two words, right?
Yeah, it's umid itself can exist on its own. So root, morpheme. Par it always has to be attached to another one, the morpheme. So I'm impressed that you were able to go deeper in the morphology, and you did it again in the next in the table. On the next slide, you wrote guftagu ki, which is the last line, which it's two. It's guftagu, which is conversation, and ki, which is a morpheme on top of that. So in the is just the key part. So you got guftagu ki. So I can see where you got the improvement, where you managed to find the morphemes inside, translate, and then get a context sensitive translation. But I noticed that you struggle in the Arabic where the proper nouns and common nouns occur together because people's names have common nouns in them. So, and we know this, Abd means slave, but we also use it as a name, Awadallah, Abdul Mahmud, all of those. So I wonder if your struggles are occurring because names have morphemes that have common noun meanings as well. And maybe therein lies some of the trouble.
So this is a very good question. First, the morphological candidates are generated using stem-based translation. So we don't know any stems for both language, but Christina has an approach to learn the stems based on the word alignment. So from the word alignment, we learn these similar stems, and then we generate stem-based translation, which is very, very rough translation. It can be good, it can be bad, but it can give you an idea. Given the context, we may pick it or not. So for that, it can work very well with linguistics alike prefix suffix. For people name, since this is part of a name and it is actual, it is less likely to make a collision with the actual words, because like the actual words using that is less frequent in the data than the people name. But for the case of the Urdu, when you have the actual prefix suffix, I think using word alignment, it will be learned much easier. Maybe that is the reason for having that. Yeah.
You have a lot of good progress even with this. That's what will come next. I'm excited about what will come next.
We're hopeful that we can learn those as features in that representation, and we get it rid of having to manually generate candidates, because it can be similar to each other still, right? So we hope that in the Urdu case, the features would learn that this piece is really related to that part, not to that part, and so on. Now we are doing it in more like hacky way, but we hope that we can learn that features in more systematic way.
I'll use it once. If it ever shows up in the Bing translator, I'll use it.
Yeah, you should use it now. So
on my hands on it.
So this work still, it is early research. It takes a lot of computational resources to compute that tables and that extensions. So even for Bing translator, we would have to generate that offline. Like for example, we take a lot of data, generate new tables, and be available for the user. It wouldn't be on the fly for now until we have more cheaper clusters and the computational resources can be on the fly, but
Next year.
maybe.
Okay, in both these cases, you're going into English, which is morphologically poor.
Going
How
to
do you
English.
predict your results will be going into more morphologically rich language?
Yeah, good question. We didn't try anything in the other direction. We should try that. Yeah. I don't know. It's interesting to try, but we didn't try.
Urdu to Arabic would be interesting.
Yeah, but you might have like less cases where this would trigger, right? Because if it's simpler, then the vocabulary is smaller, so you'll have fewer unseen bigrams.
So you will not have the issue of morphological variant. It will not be that important because you are going the other way. But even for English to Arabic, going like even with very large systems, we have the problem of not able to generate phrases that is highly morphologically inflected. Like when you say in Arabic, pose their box, for example. That's one word in Arabic. And so we can generate that even in Arabic form, and we resort to simpler forms. So if you can catch that is one to many or many to one, it can help. But as the question, we didn't try that, but it's an interesting direction.
So it seems also that it's not just that you're generating more things basically for your phrase table, but maybe the previous page has a couple examples of your reordering model, right? So it's not just that you've got a drop-in replacement for phrases, but there's a much sort of bigger set of interactions that's happening. So are you explicitly doing anything about that, or are you training?
Both are hierarchical reordering model. Michel Gallet hierarchical reordering models.
But how are you generating that? So right now it's the graph propagation gives you what you extract your phrase tables from, right? So how are you generating your reordering model?
Reordering model was trained on the small barrel data.
Okay, so the reordering model is just basically given now a slightly different set of inputs, it's doing what it would have done anyway if it had happened.
Yeah, but since we have new phrases and we retune our parameters based on the new phrases, it can, like in this case, some of those parameters will be different rather than the others. So you change the parameters and that can change a lot of the game. But it's not too much difference in terms of reordering,
Well,
maybe.
it's not too much different, but it is interesting to see that these small, what you basically planned as being small drop-in replacements for like bigrams, are propagating effects that are quite sort of substantial.
That can affect the brevity penalty, for example, the phrase length penalty. All those can be affected when you introduce longer phrases.
Yeah, but it's such a small trigger is generating this, and that's interesting.
Sorry for that. Thank you. Sorry for that.
Okay, we're going to move on to the next talk. This is Fei Xia. I guess most of you know Fei. She was one of the founding faculty of the CompLink program at UW, starting in 2005. Actually, we've known each other for years. If you happen to know Fei, one thing you know about her is she's tireless. She's dedicated and maybe relentless. These are all good qualities, actually. If you've ever worked on a paper with Fei, you know exactly what I'm talking about, or if you're a student of hers. Anyway, I talked about the IBM connection already, so I'll stop with that. She's currently an associate professor in the Linguistics Department at UW, so I'll hand it off to Fei at this point. I was going to say more, but we need to go.
Right. Thank you very much for the introduction. So I want to say a few words about my co-author. So Yan was actually a student at the City University of Hong Kong, and he went to UW as a visiting student a few years ago, and we worked on this together. And after he left, we continued the collaboration. After he got his PhD, he actually went to Beijing, joined Microsoft over there. So that's a connection. So today I'm going to talk about domain adaptation. And I think we actually have several experts in this room for domain adaptation. The goal here is really to say that when you train your system on any label data, and if you test it on a different domain, the result can be really bad. The goal of domain adaptation is to kind of bridge the gap, right? And there has been a lot of work on this, and I'm going to cover some of those quickly. So in this talk, I'm going to kind of discuss a few recent studies we did on domain adaptation. I'm going to first talk about related work, and then we basically tried 3 different approaches, and I'm going to go over each one, and for each one, I'm going to show you some results. So for related work, one way to look at this, because there's so many work, is to look at assumption. So for domain adaptation, you always assume you have a large amount of label data in the source domain, and then the target domain is where the test data come from. So for this, you can either have no labeled data in the target domain, that's called semi-supervised setting, or you can have a small amount of labeled data, that's called supervised setting. Right? And then you might have additional unlabeled data either in the source domain or in the target domain. For main approaches, if you look at the supervised setting, here I just list some of those. It's not supposed to be complete. For example, model combination, what you do is you build a model for each domain, and then you give each model different weights depending on the similarity between the source domain and the target domain. Or you can give weights to instance, not the models, right? Or you can use a so-called feature augmentation, where you make a copy of the same feature. So basically, for each feature, you make 3 copies, one for source domain, one for target domain, and one for the general domain. And then the last one here is called structure correspondence learning. The idea is to say when you have different domains, you want to learn the relation between features in those domains. Right? And there are more than this. For semi-supervised learning, we start with self-training and co-training. That's pretty standard. And then there has been a lot of work on training data selection. And here, actually, 2 authors are here already. And the idea here is to say that you want to select a subset of training data that looks closer to the target domain, and then you train your model only on this reduced text set. And then we did something on the last one where we actually use unlabeled data. So the idea there is to say, okay, you can actually use unlabeled data, and then you can kind of add additional features, and I'll give you more information about this pretty soon. So now let's look at the first study we did. Now let's look at 2 existing methods. One is training data selection, and one is feature augmentation. There are pros and cons. So for training data selection, the pro is that because you only use a subset of data, you can speed up training. And this is really important for some application. For example, machine translation, when you have like millions and millions of sentences, right? And the performance, in fact, when you use a subset of the training data, you can actually get better performance than using the whole data set. The cons here is that for certain applications, you might not have a huge amount of training data. Then when you select a subset, the unselected part is kind of ignored, right? So for some applications, you can actually get lower performance, and I'll show you some example. Right? Now for the second approach is this feature augmentation, right? The pro here is that it's very easy to implement. You just make 3 copies of everything, right? And normally you get some improvement. The cons here is that it requires that you have label data in the target domain. So this is in the supervised setting, right? And for certain applications, you don't have label data in the target domain. And also because you duplicate the features, you basically triple the number of features, and that could cause a problem. So how do we address this limitation? This is actually a very simple idea. So the idea here is to combine both, right? The way you do it is that you use training data selection to kind of look at your source domain data and divide it into 2 subsets. One is you select those, one you don't select that, right? And then for the one you select that, you assume those data will be closer to the target domain. That's the reason you select it in the first place. Right? Now you can just apply the standard feature augmentation to those 2 pseudo domains. The advantage for this is that for training data selection, you can use the whole data set, right? And then for feature augmentation, you can pretend you have label data from the target domain. So it's a very simple idea, but we actually show some improvement. In this case, we look at 2 tasks. One is Chinese word segmentation, one is PS tagging, and we use a standard baseline, right? So we use a CRF taggers. When you use a training data selection, you always have to decide what similarity functions you are going to use. And here we tried 2, and you can try different ones. One is based on entropy, and one is based on coverage. Because what I mean by coverage here is to say that for word segmentation, one major issue is OOV, right? Out of vocabulary words. So what we do is that when we select the sentences from the training, the source domain, we actually want to cover as many n-grams in the test data as possible. So that's what it meant. I'm not going to go into the detail, but I'll just show you the results. So we tried this on the Chinese Pantry Bank 7.0. Right? It has more than 1 million words. The interesting part about this corpus is that it has 5 different genres, broadcast conversation, broadcast news, and so on and so forth. So we choose one genre as our training test data, and then the training data will come from the other 4. Right? To just show you the result here, so here you see some lines here. The baseline is this. That means you just, so this one is you use only training data selection, right? So this is you use a whole training data set, right? So that's this line. And then here, this x-axis is the percentage of training data you use for your training. So you can imagine when you use 10%, the performance is actually worse, right? So this bottom line here is that when you use a random selection to select 10%. And then this AEG, this is a measure that we use entropy-based selection. And this blue line is when we use this coverage-based selection. But the point here is that both selection methods outperform random selection. That's not surprising. But when you use less than, say, 60% of data, the performance are actually not better than the baseline. Because for this data set, we don't have a huge amount of training data. So therefore, throwing away any data, we actually it hurts the performance. But if you go up a little bit more for training data selection, you can get something better than using the whole data set. Right? So that's when you use training data selection only. And now suppose you use both, right? So in this case, you use training data selection, and then you use a feature augmentation, right? This is for PS tagging, so that's a baseline. I think the baseline is you just use 100% of data. And here, this x-axis, once again, is the percentage of data you select. But now when you select 10%, it does not mean you throw away 90%. It means you pretend the 90% come from the source domain. So you still use a whole 100%, but you give them different weights. So in that sense, it's like the instance reweighting, something like that. But it's just that you do the training data selection first, and then you divide your data into 2 sets, and then you use a feature augmentation. So you can see you can get a kind of nice improvement. And the next one is for word segmentation. This is actually interesting in the sense that, once again, this one is the baseline. That means you use 100% of data from the source domain. And here is when this one is you use a feature augmentation, but this line means that you duplicate every feature. So when you duplicate every feature, the performance is it's actually not much better than the baseline because you just have too many features, right? But this line is that when you duplicate only certain kind of features, right? For example, for certain features that are not localized, so you only increase the number of features a little bit, not too much. So that way you don't get hurt by this explosion of feature numbers. So you can see you get some improvement. And this is actually what we want to see initially, right? We want to say when you select, say 10%, 20%, you get a big improvement. But once you select more, suppose you select 60%, it's actually not much better than your baseline because it's no longer that different how much you select from your training data. So that's the first experiment. Right? Now I'm going to move on to the second one. So the second one, we try something different. So in this case, what we are saying is that the setting is that suppose we use a semi-supervised setting, means you don't have label data in the target domain, which is the same as the previous one. But the idea here is to say, what if you have an unsupervised method? Right? Sometimes unsupervised method can complement the supervised method, right? So, and the way we are using that is to say, basically the idea, the intuition is just to say you run unsupervised learning, you get some results, and the results will not be reliable, but then you treat those decisions as features, and you use your source domain data, which is labeled, to learn how useful those features are. And in this study, we also look at word segmentation. And then for unsupervised learning method, we use this DLG. I'll give you a very quick introduction about this. The method itself, the DLG, is actually not that important in the sense that you can replace this with any method you want to use for unsupervised learning. But just to give you some idea about what's going on here is that for word segmentation, as I mentioned, the main problem is really OOV, right? You have all those unknown words in your test data. And then one way you can measure this is to look at a certain string. So let me explain this measure a little bit. So suppose X is a corpus, right? And now you want to represent this corpus with some description length. So DL means description length, right? It's really n is the size of your corpus multiplied by the entropy of the corpus. What it means is that suppose you have a vocabulary from this corpus, and you are saying, okay, I will just calculate the entropy for this corpus, and that's your description length, right? The DLG is really a function of a string. So here, S is a string. It's a string in your corpus. So what you do is to say, you have my original description length for the corpus, and now what if I replace this string with ID? So in the sense that you say, okay, this string, I treat this as a word in my dictionary, and now instead of having this whole string, I only need an ID to represent that. So now you get a new corpus by replacing the string with the string ID, but you still need to add a string to your dictionary. So there will be additional cost when you add something to your vocabulary, but overall you get a gain, right? Because now the description length will be shorter. If you don't get this part, it's okay. But the intuition is to say that the longer the string is, the more frequent the string is in your corpus, the higher the score is, the DLG score will be. So therefore, you can imagine if you want to do unsupervised word segmentation, what you can do is that suppose U is a string I'm trying to segment. Then what I can do is that I can try all possible ways to segment that, right? And now for each segmentation, I look at the string in that segmentation and I calculate the score, and then I can have certain kind of weight for this, but eventually I will choose the one with the highest score, overall score, right? So therefore, you basically prefer long string and you prefer, frequent strings, and you want to treat those as words. So that's unsupervised learning in this case. But the problem with this is that sometimes you have a phrase, like for example, Hong Kong. I mean, Hong Kong you can argue whether it's one word or two words, but sometimes you have certain kind of correlation, like could you please, right? So those will not be a word per se, but they are very frequent and they are very long. So you can treat those. I mean, if you use this method, it will treat this as one word instead of multiple words. So unsupervised learning does not really work that well, but it's very good at finding those kind of new words you have never seen before. So what we do next is to say, okay, now let's use that finding for supervised learning. So what we do is that our baseline system is just a word segmentation, word segmenter. So we treat this as a sequence labeling problem. That means for each character, you decide whether you want to add a break or not. And here B1 means the first character in a word, B2 means the second character in a word, and so on and so forth. So you can treat this as a POS tagging problem. And then we use a standard feature set. There's nothing kind of strange about this. And now when we add the DLG feature, what we do here is to say, okay, let's calculate the DLG score. Right? So what you do is that take the training data and take the test data. And for training data, ignore the word segmentation information. Assume it's unlabeled, right? Now you get a union. And for this whole data set, for every character n-grams, we want to make it shorter, so there will be some length constraint. But other than that, for every n-gram in this data set, you calculate the DLG score. Right? And then you kind of say, let's see for each character in my training data or in my test data, I want to form a new feature vector. So this is the same feature vector as before, but now I'm going to add some new additional features. So those features basically represent what is the decision if I use unsupervised word segmentation for this, right? And then you learn how useful those decisions will be. Right? So for example, suppose the sentence is C1, C2, C3, C4, C5. You have 5 characters. And now suppose we form the feature vector for C3. Then what you do is that you look at all the n-grams in a string that contains C3, right? And now you collect the DLG score not from the sentence, but from the whole corpus, right? So you get the DLG score, and you take the log, and you take the floor, so you get an integer here. And then you say, okay, suppose C3, and then this last column is the tag for C3 in the string. So here the word, if the word is only C3, then the tag for that will be S, means it's a single character word. And suppose the string is C2, C3, then the tag for that is going to be E. E means the last character in a word, and so on and so forth. So basically you collect this, right, from your training and test data. And now what I'm going to do is to say, okay, suppose C3 belongs to a word of length 2, right? Suppose. Then there are 2 possibilities. It's either C2, C3, or C3, C4. And I look at those scores, and I just make a decision. I choose the highest one, right? So if the highest one, the score will be 2, and the tag for this will be E, right? So I'm saying if C3 belongs to a word of length 2, then the decision based on unsupervised learning will be the tag for that will be E. And then the strength for that will be 2. So I create a new feature. Right? You can try different ways to create a feature. It doesn't really matter. But the point is that you add all those additional features and add it on top of your existing features for supervised learning. And now, just to show you the result here. In this case, the test date genre is BC. So BC is broadcast news. And then the training genre will be either BC or something else. So if it's BC, then this is trained in the same domain, right? So if you use the baseline here, that's 93.9. When you add the DLG score, although it's the same domain, you still get an improvement, right? And the web is out of the other 4 genres. Web is closest to BC when we try this domain adaptation stuff. So that means if you use a baseline is this number, and if you add the DLG, you get some improvement. And NW is newsware, I guess, something like that. And this domain is most different from broadcast. So you can see the baseline is much lower, but when you add the DLG, you actually get a bigger improvement. So that means when the training domain and test domain are more different, you actually get a bigger boost from adding unsupervised learning results. You can also combine segmentation with POS tagging, right? I'm going to skip this part, but it's just that when you do this, you can also add a DLG on top of that. This one is just to allow us to compare with existing work. So you can see those are some previous work. This work was published like in 2012, so that was the latest result at that time. So you can see this is a result for segmentation. This is result for both segmentation and POS tagging. So when you add the DLG, you get some improvement, and you always get some improvement. So eventually, the result is about the best result at the time. So that's a second approach. The third one is really the most recent one, and I think this is actually interesting in the sense that here we are not talking about 2 domains. We are talking about 2 languages, right? So the idea is to say, what if you have 2 languages that are closely related? Right. What happened is that very often we know that creating corpora is very expensive. So we have resources only for certain languages, right? But there are fewer resources for Asian languages for obvious reason, right? First, there's no money there, right? So nobody wants to work on that. Second, you don't have a lot of data, and so on and so forth. So the idea, right? You don't have, sometimes you have one speaker or no speaker. So the question is that can we actually improve the NLP system for Asian language when you have resource for modern language? Okay. So we want to kind of just take a look and see what we get. In this case, there has been some previous study. So here I list some of those. And most of those studies are based on spelling normalization. So for example, in Middle English, you spell a word this way, but the corresponding part is you spell that way. And here we want to do something slightly different, right? So the language pair we used is archaic Chinese and modern Chinese. And once again, we focus on word segmentation and PS tagging. So the idea here is to say that you want to find the properties shared by those two languages, right? And therefore, you want to kind of explore that information. To just tell you how different the Old Chinese is, right? So if you look at, based on this book, of course, there are different ways to divide Chinese, but there are 4 arrows for Chinese, right? So here it gives you the time period. So basically, this archaic Chinese was spoken before 200 AD, right? And modern Chinese, you can look at the difference. It's like a huge difference. And as a result, modern Chinese speakers will not be able to understand archaic Chinese without training. For example, I remember when I was in middle school, we actually have to learn how to understand those texts. And that's my favorite subject at the time, right? Because anything else I learned in that Chinese school is totally useless. That's actually a separate story because the way they taught Chinese, it was awful. But anyway, that's the reason I remember, right? So it's like those languages are really different. And what we did is that we look at one book. So this book is actually a collection of papers or theses written by this guy and his retainers. In this time period. The interesting part about this book is that it has 21 chapters covering a wide range of topics. So you can imagine they are from different domains, and so therefore it gives you a very good picture about what people are were interested at that time. Right? So we have this book, and then my colleagues, they create these corpora. So they did the word segmentation, they did the PS tagging for that. And the way they did that is they start with the Chinese Pen Tribune guidelines, because every time you create a corpus, you need the guidelines, right? So they based on the same principle in the sense that when you talk about word, there are actually different definitions of words depending on what you are trying to do. So they follow the same principle, but the decision can be different. For example, this word, right? This string, I will say this string. The first character means country. The second character means family, right? In modern Chinese, it's one word. It just means country. But in Old Chinese, actually, it's very often used as 2 words, right? So it's really country and family, right? It's interesting debate why country plus family become country only, but that's a separate story here. That's Chinese philosophy, right? Country is always more important than family, which I kind of disagree. But this is just the size of the corpus, right? So the number of characters, number of words, number of sentences, and the average sentence length. Now the question is that suppose you have resource for modern Chinese, can you use that to improve the performance? What we did is that the training data, we assume we have some label data for this old Chinese corpus, but we also have modern Chinese corpus. So here we use Chinese Pen Tribune version 7. And then for test data come from this old corpus, right? So we use 5-fold cross-validation, 4-fold for training, and 1-fold for testing. You can imagine what kind of baseline we have, right? We can just use the in-domain data only, right? So in that case, it's the old Chinese only, or you can use the modern Chinese data only, or you take the union, right? So that's the obvious baseline. So for our approach, basically to tell you the story right now is that if you just use a union, you actually you don't get any improvement, right? As you can imagine. So what we want to do is do something slightly more clever than that. So we want to find properties shared by those 2 languages, and then kind of represent those properties as features, and then build a system. The question is what properties are shared by those 2 languages? So we did some study, right? In this one, it's just some statistic, but the most important part is here, the average word length. So you can see for modern Chinese, the average word length is 1.6. For Old Chinese, it's 1.1. Right? And it's actually consistent with our understanding about the Chinese as a language. So it goes from monolingual, a language of monosyllable words to kind of more kind of words longer lengths, right? So basically, you can see this is a kind of difference. So you can imagine for word segmentation, if you want to do, you want to build a word segmenter for all Chinese, you can just add a break, after every character, and you'll be 90% correct. So that's one thing. And this one is just to give you a breakdown, right? So you can see for all Chinese, 86% has only one character, right? So that's percentage of word tokens with only one character and so on and so forth. So for modern Chinese, it's kind of half has only one character, and about half has two, and then you have a kind of tail for longer words. Now, if you look at POS tagging, so this is the percentage of word tokens with that POS tag in this corpus, right? So for NN, that's noun, right? So PU is punctuation, and VV is a main verb, and so on and so forth. So AD is adverb. So you can see for the first of 4 categories, they are about, they are very frequent in both, right? That's not surprising. But I want to show you something else. There are actually many POS tags that do not appear in Old Chinese. Some of those are due to content. Right, you can imagine the 2 corpora, they're talking about different things, like there were no URL at the time, there were no foreign words for obvious reason. But then there's something else. For example, ba, right? Ba is a POS tag for this word ba in the so-called ba construction. And it turned out this construction did not really appear until like 200 years after this book was written. Right? So there was no construction. The construction was not there at the time. And similarly for those POS tags, they are for this de, right? So there's this special Chinese character, actually there are 3 that are all called de, right? And they actually have a different POS tags because they behave very differently. And that's also a kind of new phenomenon in the sense that they did not really appear, they did not have that usage until much, much later, right? Similarly for aspect marker, right? It was very different. So therefore you can see if you just use the POS tag distributions, they actually look pretty different. So therefore, if you build your POS tag model from modern Chinese and use that for, old Chinese, the result could be really bad. So will there be anything that they actually share, right? One thing they actually share is really the character set. So what I mean by the character set, I don't mean the set of the characters in the sense that if you say how many characters are there in Chinese, nobody knows. Like, I don't think there's any single person in this world really know, right? The conservative estimate will be something like 60,000 characters, right? But the normal daily conversation, or if you look at even the Chinese country bank, we count the number of characters is only 5,000. So there will be, if you know 8,000 characters, you'll be fine, right? But then, very often I will see people's name that I don't know how to pronounce because I just don't recognize that character. I don't think there will be a single person in the world know all the characters or know how many characters are there. But then the meaning of characters normally don't change that much over the time, right? So this is one character means top or up. It can appear in this word means top, right? So that's a localizer. It can also mean this one means climb up, right? So this one means climb up. And this one means Shanghai, right? So this is just a name. So you can imagine this character can appear in different words, and those words will have different POS tags. But now, the meaning of the word, the character, actually does not really change that much over the time. Therefore, if you say for the meaning, sometimes it corresponds, the POS tag very often is related to the meaning. If it's action, very often it's a verb, right? Of course, it's not always true. But now, suppose we use the so-called C tag. This is just a POS tag of a character. So what we do is that we say, okay, for each character, there will be one or multiple tags for that, and we want to learn those tags. So here is to say, let's just collect those things. We actually don't have the the C tag labeled in our corpus, so we just make a very simple assumption. So we are saying, suppose this word is LC, right, localizer. We just assume each character also have LC as the C tag for that. And now you just kind of count your corpus and kind of rank that by frequency. So you can see for this character, most time is part of a localizer. Right. So that's for the modern Chinese, and that's for old Chinese. So you can see, although the frequencies are different because the corpus size are very different, but if you look at only the top one, that's like the core meaning, they actually remain roughly the same. So we are saying maybe that's something they actually share. Right? So we'll call that C tag. Right? Also, something shared by the 2 languages is a word formation pattern. Right? So for example, suppose a word is a noun, and suppose it has 2 characters, and suppose the C tag for each one is NN, so we'll write this as this pattern. So here I give you one example. So this one means politics, and this one means place, and politics, place means government, right? So there are different kind of word formation patterns. And here, that's the raw count in those corpora, and this is percentage. So you can see, although the percentages are not so similar, but you can see similar patterns in those 2 corpora. So maybe the patterns will also be useful. That means the C tag can actually give you some information about the PS tag of the whole word. Right? That's the idea. Now let's see, just to summarize, the 2 corpora actually differ a lot with respect to word length distribution or PS tags, but they share a lot of information about C tag and also word formation patterns. The hypothesis we have is to say, now if you just add CTB directly to your training data, very likely the performance will not improve. But if you add C tag as features, maybe you will get some improvement. Just to show you the result, once again, we run word segmentation and PS tagging. And here, just to show you the size of the training data and test data. And here is only for the old Chinese. I did not include a number for CTB. CTB, of course, is huge. It's like 1 million words, right? So we use CTB only at the training stage, as you can imagine. This one is just to show what tag set we use, right, when we do word segmentation. So we call those tags as position tag to distinguish that from the C tag, right? C tag is a PS tag of a character, and position tag is just to say whether it's the beginning of a word or the end of the word, and so on and so forth. We use a standard CRF tagger for this, and then we just use our standard feature set, but now we add the C tag. And the C tag, the frequency of those C tags will come from the training data only, right? Otherwise, it will be cheating. So now this is we can record those basic features. Those are just character, unigram, or bigram. This is a C tag feature. The 0 here means we look at the current character and we look at the most frequent C tag for that character. And the DLG feature, I mentioned DLG before, those are just additional features we used here. Just to show you the number here, let's look at the first group here. So now suppose you only use a basic feature. BF means the basic feature. So it means you only use a character n-gram, unigram or bigram. So this one means you use the basic feature from the old Chinese corpus only, right? So that's the baseline. And this is if you use the data from modern Chinese only, CTB, right? So you can see this result is awful. It's like awful. It's worse than the baseline when you just add white space after every character. And this is result when you just take the union, right? So it's not that awful, but still it's worse than the baseline. And also we will say, okay, for the basic features, we will only get it from the old Chinese corpus. And now what about C tag? So when you use a C tag from the old corpus, old Chinese corpus, the result is actually a little bit worse, not much worse than this. And the reason for this is that this corpus is pretty small, and the C tag, because we use this very simple way to get C tag, is not really reliable, and so on and so forth. But if you get it from the Chinese pantry bank, the modern Chinese, the improvement is small, but it's actually it's not getting worse, right? And now if you add a DLG feature, you'll get some improvement. So you might say, oh, maybe there's really no improvement. And the reason for this is really you have more training data. What if you have much less training data from the old Chinese, right? So for this experiment, what we do is that we look at the training data for old Chinese, and then we only take a small percentage. Instead of 100%, we take, say, 10%. And now you can compare the performance. So this line, the red line, is when you only use the old Chinese corpus. And this one is when you add the C tag feature from CTB. And this is the line where you add the DLG feature, right? So you can see when you only use 10% of training data from the old Chinese corpus, you actually get a much bigger improvement. Because now you really have very little amount of data. So for modern Chinese, although it's very different from old Chinese, but it gives you a bigger boost. And similarly, for PS tagging, we get basically the same kind of result, right? So for the feature set, the same thing. It's just that we use a word unigram and bigram, right? And then you can add the word affix. For Chinese, it's hard to decide whether something is affix or not. So what we do is that the prefix is just the first character of a word, and the suffix is just the last character in that word, right? And then the C tag of affix is just to say what is the C tag of that character. So the same kind of result, right? So if for basic feature, if you only use the old Chinese corpus, that's the baseline, right? When you use the modern Chinese, you get a worse result. When you use the union, it hurts, right? And now when you add the C tag, you get some improvement. And if you use the C tag actually from the modern Chinese, actually get slightly bigger improvement. And once again, if you add FX feature, you get some improvement. The same chart as before. So in this case, when you have less training data from the old Chinese, you get much bigger improvement here, right? So it's like 4% here when you just add data from the modern Chinese. So what it really means here is just to summarize. Those two languages, I mean, some people will say, oh, they are really the same language. We don't want to argue about that. I will say they are different languages because I cannot understand this one without learning what I learned in high school or middle school. But they are actually very different, right? With respect to the word length or PS tag distribution. As a result, if you just add modern Chinese data directly, it does not really help. Right. But if you find what they really share and then use that as features, you actually get some improvement, especially when you have very small amount of data from Old Chinese. So to just summarize, I kind of introduced 3 different methods, and they kind of look at different angles, right? So the first 2, we assume semi-supervised setting, which means you don't have label data from the target domain. So we can either combine those, right? This is really a very simple idea. Or you can use unsupervised learning and then use that as a feature to train your supervised method. And the last one, look at 2 kind of closely related languages. And I think the key point here is really you have to find out what they truly share because they can be very different. And for future work, the question is that I'm sure there are other features that we can use. And we want to identify those. And a more interesting question is that whether those features can be identified automatically without prior knowledge of the domains or languages. In the sense that if you give me the domain and give me the data, can actually know without using my kind of expert knowledge to know what features I should look at. And then we want to apply this to kind of other tasks. Thank you.
Seems ancient Chinese and modern Chinese are in this unique relationship in that one is a descendant of the other. A more interesting case, I think, would be, more applicable would be ones where they're sister languages, where they actually share a common ancestor. Now, finding an ancestor where you actually have good data like this for it would be difficult. So you might, in some families, be able to find that. So being able to then establish a relationship with that ancestor and then pivoting through that ancestor to some other modern language that is more resourced would be interesting because then it's directly applicable to a language that's still in use. The problem of the ancestor, I guess, you could get into a reconstruction kind of thing too, where you could basically, and this has been done a lot, obviously, in linguistics, is reconstructing some common ancestor. If you can then associate with that reconstructed ancestor, and then somehow use that information from that ancestor to help inform descendant languages, that would actually be very interesting.
Yeah, and I'll just say that there's this one, actually, we all know Penn, English Penn tree bank, right? But there are actually a Middle English tree bank done by Penn. And also not only Middle English, I think they also have Middle, maybe German or High German, something like that. So that they actually have kind of Asian, not Asian, but Middle languages for several languages. So I think that would be interesting. Suppose you have Middle English and Middle French. I don't really know.
I think the problem there, okay, so you could use similar techniques here. Again, the problem is what are the characteristics, what are the features that you need to reconstruct a tagger or something for one of these ancestor languages. But in a way, though, what are the descendants of modern what's the Middle High German or whatever it was? Middle High German. What are the ancestors? Well, there's more or less one. Well, I guess there are multiple ones. Never mind, because it's not just High German. But are we building taggers for Bayerisch or Plattdeutsch or something? But you'd almost need to go further back in time. What's nice about this is that you're going very far back in time. I mean, this is 2,000 years ago. That's actually it's phenomenal.
Thank you.
There's a language emerging in Kenya called Sheng, which is a slang version of Swahili and English mixed together. They were going to call it Seng, but they can put DH in there. But anyway, it's Sheng. And the corpus for Sheng comes in the form of what's cool, social media, advertisements, pop songs, but it's always changing because it's slang.
Right.
And it's current. So if we had to take a snapshot of Sheng in time and use established corpora for Swahili and English to try and tag Sheng,
Yeah.
forgetting the fact that it's always changing, would this approach be useful? Since Sheng is still considered resource poor right now, but
Right.
maybe, I don't know, maybe if for any particular snapshot of Sheng is resource poor because it changes.
Yeah, I think that the key kind of challenge or something I really want to look into is to say, can you really identify those properties kind of automatically or without knowing the language? I think the reason we kind of look into this is that as a Chinese speaker, I have this intuition that the character meanings do not really change so much. But on the other hand, I think if there's any way to kind of find out what features are truly shared, I would imagine one can definitely run some experiment to see this. And also it depends on what kind of change. Is just spelling, is just the alphabet, or is that the grammar? Like what is changing? For example, what we did here might not really, I should not really say this, but I'm just saying for parsing, I would imagine because the word order changed so much, but there could still be something that is continuing. But I'm just saying it's not trivial to find out what exactly are shared by languages. I think that's kind of
Multi-heritage languages which come in from two different language families, like bastard children or things like that. Like you weren't expecting this language to happen, but it happened.
Right.
Now you have it. But one parent of the language is English, and
Right.
one is Swahili. Or for Urdu, for example, one parent is Arabic and one
Right.
parent is Hindi. What do we do now? And when there's another one, Persian, the third parent. So could we approach it even then and say, oh look, we have Persian corpora, we have Hindi corpora as well, sort of. We have Arabic corpora. Now we can get Urdu corpora.
right. I think one thing I'm always fascinated about, but I never really got time to look at, is language code switching. In the sense that when you code switching, here you only talk about two languages, but when you have multiple languages, the question is that what is being switched, right? Is that a word? Is that the syntax? What is being switched? So now when you have a language that comes from multiple parents, which part you get from parent one, which part you get from parent two, and what's the interaction? I think those will be very interesting questions to look into. But that's something that I always feel, okay, when I retire, I can look at that. Or when I have free time, I can look at that. But that's something I'm always fascinated about. Yeah. David?
I don't think that anything in your methodology says that these have to be sort of parent-child relationships.
Right.
Do you have any plans to do this on maybe very closely related, something like Azerbaijani and Turkish, which are not quite mutually intelligible, but really close?
There has been a lot of work done for related language pairs. For example, this Google tree bank, universal tree bank, I guess maybe you heard of that already. So basically they have, the version 1, they have 6 languages, and for version 2, I think they have 9 languages. And then what they did, you can imagine, you can train on one language and then just use that model, but do the unlexicalized version, means you only have the rules but no lex items, and parse the other one. And conceptually, you say if those two languages are very similar, then the performance should be better. And that's consistent with some finding they have. But I think definitely you don't have to, the two languages do not have to be in this kind of ancestor, descendant relation. It can be related. And now the question is that if you know they're related, certain things that are shared, then you can use that. But certain things they change already. For example, one is SVO, one is SOV. What do you do? Do you kind of do pre-processing, or you do it in the model, or you do it in post-processing? How do you incorporate knowledge you learned? And I think that will be very interesting in the sense that you can do the first run knowing nothing about the languages, but after the first run, you actually know something about the language, and then you have that knowledge, and then how do you incorporate the knowledge you just learned? It's like what we did, right? It's like from olden data, you get some information about the grammar, and you want to have the second run to do something better, right? Because you know the language already. But the issue is always the time is not my interest. I'm interested in a lot of stuff, but in the short term, I might not be able to work on that. But
You know, it's actually a really interesting case because with the Odin data, pulling the data from all the different languages,
Yes.
right, 1,200 languages,
Right.
the alignment data basically helped inform, for languages that didn't have much data, you could
Right.
actually use the alignment information from the other languages to help inform
Right.
the tools you were developing for the
Yeah.
low resource ones. So
Yeah.
there is, even if the languages aren't related,
Yeah.
there is information you can pull in if you have enough data
Right.
and enough information from, enough signal to draw
Yes.
from.
It's almost like when you say nearest neighbor, right? Here we're talking about neighbors. Then you just use all the neighbors and assume the distance is different and somehow take that into account. So therefore, in theory, we don't really require any kind of relation between the languages. It's just the closer they are, the more likely you get some
More
improvement.
shared features.
Yeah, right.
Yeah.
More shared features. Right. Right.
Kind of backtrack to a more technical question. In the first portion of the technique, when you were doing training data selection, how were you actually deciding which portion of the 10% of the training data to use?
Oh, which portion of 10%?
Would,
Oh, like you are saying, is that 10% or 20%? Like, how do you decide?
well, yeah, if you're taking, say, 10% or whatever percent, how do you decide which?
Oh, that one. That's where you have to define a similarity function. So what you do is you have training data and you have test data, and then you compare how similar they are. For example, you can use the entropy, right? And
Right.
saying I build a language model based on one domain and then test the other one. So Will has a very good paper on that. So there are a bunch of, you can use any similarity function you want to use, but the idea is to say you look at each sentence in your source domain and compare that with the target domain data and see how close they are. And then you define what you mean by close.